both of them. So assume that if VB is going to change by a small amount with temperature, assume the temperature is changing, VB is also changing. Since VB is going to change, VD is also going to change. Therefore, they will cancel each other. If VB is going to change, VD is also going to change by the same amount, which means that the transistor is going to have nil effect because of the change in the VB with respect to temperature. So this equation is taken from the fixed bias circuit. So I'm going to rearrange this and I'm going to get what is IC. So this equation derivation I'm not going to explain you again. You can refer to the fixed bias circuit for the expression for VBE. So VBE is VT minus VT is V Thevenin's voltage minus some constant into IC plus some constant into IC naught. So from this equation rearrange and get the value of IC. So bring all the terms to other side, take LCM, take reciprocal of the fraction, you should be getting what is IC. Okay, now see here, in the IC, you have beta into VT minus VBE plus all the constant term. If you consider this base side, additionally you have a minus VD, right? Additionally you have this diode here. So in this expression, you will have VT minus VBE minus VD. So additionally, you can see one more term coming because of this diode. So the variation of VD is same as VBE. So collector current will be insensitive to variation in VBE. So it is going to be same. The variation in VD and VBE are going to be same. So this is not going to affect your collector current at all. You can see the polarity here. It is plus, it is minus. And here you see it is minus, it is plus. So if VB is increasing, VD will also be increasing in the same way, but in the opposite way. So when you add the effective voltage, it will become zero. So whatever change in VB is going to happen, the same change will happen in VD, but in the opposite sense. When you apply KVL, you can see that. When you apply, see Vin is plus minus, VBE is plus minus, and this VD is minus plus. So I can write Vin minus VBE plus VD equal to 0, or Vin equal to VBE minus VD. So if VBE is going to increase, VD will also increase, but when you subtract, the effective result becomes 0. Okay, that is what is shown in the equation. So this is exclusively for variation in VBE. So what I do, I additionally take a diode, and I always have the diode in the forward bias condition by supplying by keeping it forward bias using a battery VDD. This will ensure that whatever change your VB is going to have, it is going to increase or decrease. The same increase or decrease will be observed in VD, but in the opposite sense. So effectively, it will get cancelled. So the VB is going to be constant across the BJT. So the base emitter junction is always going to have constant voltage. See, VB is also very, very important because VB will decide when the transistor is on. VB is the voltage above which only your diode starts conducting, right? So if VB is going to change with temperature, then you cannot predict the uh, forward bias of the emitter base junction. So that is the reason why we have to focus on VBE and ensure that VB is always kept constant. Otherwise, if it is going to vary, then it will affect the base current, it will affect the collector current, Q point will start varying. Okay, so this is one circuit where we address the issue of variation in VBE by using a diode which is kept always in forward bias condition. Any queries in this circuit? See, you have to be very familiar with all the circuits, whatever I'm showing, because all these circuits, we have analyzed it previously in one of the biasing techniques, right? So you should be, whenever a circuit is presented, you should be very clear on what is the circuit doing, where the circuit is coming, and what is the resistors and other values what we use in all the circuit. You should be very, very clear on that. So this is about variation, how I am going to compensate for variation